Okay, so as far as arc length and surface area of revolution are concerned, they sort of go hand in hand. Now, if you've taken trigonometry, there was an arc length formula in that particular class, and it kind of dealt with the circle. And if you're finding the arc length, the length between the angle and your circle, that's an arc length. S is equal to R times theta. What we're doing in this class is we're using integrals to estimate the length of a curve. So in this case, when you see arc necessarily means, it doesn't necessarily mean a circular arc. It just simply means a curve's length. Okay, so I'm going to switch to the desktop screen. Okay, and this is actually in the lecture notes section of the course. And I believe in section 6.3. Okay, this is a particular slide that talks about arc length, or the length of plane curves. So notice there's a kind of a play on words as far as arc length and the length of plane curves. Okay, and basically we know what is meant by the length of a straight line, but without calculus, we have no precise method of measuring a general winding curve. So in essence, a curve that's not straight. The idea of approximating the length of a curve running from A to B, and by subdividing the curve into many pieces. Okay, so this is that integral concept where, as far as volume is concerned, we can take the area over an interval, add that up, and that would give us the volume. In this case, we're taking a curve, we're kind of subdividing it up into straight lines. We're adding up all of the lengths of the straight lines by use of the Pythagorean theorem, which I'll show in a second. Okay, and that would give us the length of our curve. All right, so here is the formula. Now, there are actually two formulas, but in this particular course, just kind of looking at the homeworks, we're going to use this first formula. And this first formula is the arc length formula, and you're given a function y is equal to f of x, right? So we're given a function, we're given an interval on the function, right? X runs from A to B, and if that function is continuous on the closed interval, we can approximate the length of the curve by using this formula. So L is equal to the integral from A to B for the square root of 1 plus dy dx quantity squared. So remember, dy dx is the derivative. So we must find the derivative. We must square the derivative, substitute into this formula, and then integrate from A to B. Now you may ask, how does this formula actually approximate the length of a curve? Okay, so we'll take a look at this formula, how it's derived before we actually use it. Okay, so let's just say we're in the X and the Y axis. Okay, and I'm just going to draw an arbitrary curve in the first quadrant. Okay, so let's just say we're given this curve, and this curve is continuous, right? Remember the definition of continuous says that if you could put your pencil on the graph and you can trace the entire graph without removing your pencil from the paper, your graph is a continuous graph. Okay, we want to find the length of this graph, and it's on the interval from A to B. What we're going to do now is we're going to subdivide the interval Okay, so I'm just arbitrarily just drawing points here. So we're subdividing the interval. And so this would be our, let's say, x of 1, x of 2, x of 3, okay, dot, 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 and then we have x of n, right? Now, the way that the formula is derived is I'm going to take a piece of this curve. So notice we're kind of subdividing it up. So each point or each points are, we have a straight line. Okay. So let's just say if I isolate this point, these 2 points, and between those 2 points, I can draw a right triangle. Okay, so I'm actually going to blow that up over here. So let's say we have a point here, a point here. Okay, now keep in mind that this is still on our curve, but we're approximating this. All right, and what we have is a right triangle. Okay, so in our right triangle, this is what we're trying to find is the length, right? So I'm going to call this L sub I. So keep in mind from the Pythagorean theorem, remember this is our length or hypotenuse. So in that Pythagorean theorem, c squared was equal to a squared plus b squared. Okay, but instead of a squared and b squared, I actually have delta y. So remember delta y is the change in y. And I have delta x. Right? So by using the Pythagorean theorem, I can actually find this length as L sub I is equal to the square root of delta x squared plus delta y squared. Right, so that's nothing more than the Pythagorean theorem. Now what I'm going to do from this point is I'm actually going to factor out a delta x squared. So I have something that looks like this. We have L sub I. Okay, so keep in mind L sub I is this distance. That's equal to the square root of delta x squared times 1 plus delta y squared divided by delta x squared. All right, so if I were to distribute, delta x squared times 1 is delta x squared, and delta x squared times delta y squared divided by delta x squared. Those delta x squares cancel, and that actually gives me delta y squared. Okay. So then lastly, I can factor out this delta x squared. So the square root and the square cancel. So I'm left with something that looks like this. L sub I is equal to the square root of 1 plus delta y divided by delta x squared. The square root and the square cancel, so I have delta x outside of the radical. So in essence, what we're doing is we're taking all of our L sub i's, we're adding those all up, and that will give us the length. All right, so L is going to equal to the summation as I goes from 1 to n for L sub I. Okay, so in general, we would add up each one of our distances, and that would give us the distance for our curve. Okay. So putting this all together, we have the integral, right? Well, the length is equal to the integral from A to B, right? So notice we have A and B for the square root of 1 plus dy dx quantity squared dx. Okay. Right. So now when we find the arc length and when we find the area of surface, this is the root for both of those formulas. Now, in computing those formulas or computing this integral, we use some type technology. We either use a calculator, some calculus algebra system, or some type technology. Okay, in this class, we're going to approximate the lengths by using the TI-83. Okay. All right, so this is the formula. So next, we'll take an example on how to actually use the formula to find arc length. All right, and I'm going to just illustrate this by a couple of examples. Okay, we'll take a look at number 1. And for number 1, we're asked to find the arc length of y is equal to 2x squared plus 2. And I'm actually writing this down. Find the arc length of y is equal to 2x plus 2. So that's our function, 2x squared plus 2, from x equal to 0 to x equal to 2. Right, we're asked to set up the integral. Then we're asked to use a u substitution to rewrite the integral. And then we're asked to integrate. Okay, so find the arc length of y is equal to 2x squared plus 2 from x equals 0 to x equal to 2. All right, so the first thing we're going to do is we're going to find dy dx, right? Because remember that in our formula, we need the integral from a to b, so we have 0 to 2 for the square root of 1 plus the derivative squared. So we're going to find, well, plus, yeah, the derivative squared. So we're going to find the derivative, then we're going to square the derivative, then we're going to use that in our formula. So we have y is equal to 2x squared plus 2. So dy dx I'll simply find the derivative for 2x squared plus 2. So we'll find the derivative for every term. So here I'll use the power rule, right? I would take my power, multiply it by my coefficient, and that would lower my power by 1. So the derivative for 2x squared is 4x Next, we'll find dy dx quantity squared, right? So dy dx is equal to 4x. So dy dx quantity squared is equal to 4x quantity squared, which is 16x squared. Right, so we found the derivative, which was 4x. We found the derivative squared, which is 16x squared. And now we'll substitute into the arc length formula. So here I'll just jot the arc length formula. The length is equal to the integral from a to b for the square root of 1 plus dy dx squared dx. All right, so I'm simply going to substitute dy dx squared for 16x squared. Our limits for integration are from a to b. So we're asked to find the length of this curve on the interval from 0 to 2. Right, so the length is going to equal the integral from 0 to 2 for the square root of 1 plus 16x squared dx. So if I go back to the desktop screen, all right, this would be the integral from 0 to 2 for the square root of 1 plus 16x squared dx. Okay, so now we're asked to substitute u for 4x and to rewrite the integral in terms of u. Okay, so now if you were doing this problem, you could simply evaluate this in the calculator. Okay, but here they're asking us to rewrite the integral in terms of u by using a u substitution. All right, so let's see how that is done. So they specifically want us to substitute u equal to 4x. All right, so we have, and I'm just going to transfer to this sheet of paper. L is equal to the integral from 0 to 2 for the square root of 1 plus 16x squared dx. And we're asked to substitute u for 4x. All right, so what I will do from this point is I want to rewrite this integral, which is in terms of x. I want to write it in terms of u. So the first thing I'm going to do is I'm going to take the derivative with respect to x for both sides of this equation. All right. So I'm going to take the derivative with respect to x for the left-hand side. I'm going to take the derivative with respect to x for the right-hand side. So on the left-hand side, I have du dx. On the right-hand side, the derivative with respect to x for 4x is 4. I'm going to multiply both sides by dx. And I'm going to divide both sides by 4. So 1/4 du is equal to dx. So what will this allow me to do? Well, this will allow me to rewrite the square root of 1 plus 16x squared dx in terms of u. I can rewrite dx as 1/4 du. I'm going to pull 1/4 in front of the integral operator. So I have 1/4 times the integral. I'm not quite going to write my limits just yet, and I'll explain why in a second. I can rewrite the square root of 1 plus 16x squared as 1 plus u, right? So remember, u is 4x. If I square 4x, I have 16x squared. So I have the square root of 1 plus u squared. So remember that we were able to substitute dx as 1/4 du. Right, so we have now written it, we have now transformed the variable from x to u. Now here's the reason why I didn't write the limits as 0 and 2. The limit 0 and 2 are the limits for x. What we want are the limits for u, so I must change my limits. So here's how we change our limits. So up here we transform the variable. All right, we're able to transform from x to u. And here we're going to transform the limits. So first I'm going to start with my upper limit. So I'm going to go back to my substitution equation, u equal to 4x. So we base our transform on our substitution equation. U is equal to 4x. And I want to substitute x for 2 and solve for u. Right? So here I'm going to substitute x for 2. So u is equal to 4 times 2. So u is equal to 8. All right. So when x is equal to 2, u is equal to 8. I'm also going to do the same thing for our lower limit. I'm going to use the substitution equation. U is equal to 4x. Our lower limit for x was 0. So we're going to substitute x for 0. So when x is 0, u is also 0. So we have transformed the limit from x to u. Okay, so if we go back to our problem, I believe this should be 1/4 times the integral from 0 to 8 for the square root of 1 plus u squared du. All right, and lastly, we're asked to evaluate. Okay, so in order to evaluate, we're going to use the calculator. Bring that up. All right, so when you're using the calculator, you can use either one of these two functions. Okay. So I'm going to put in this first function. Well, I actually put in both just to show you that they're exactly the same. So I'm going to use the integration function. I'm going to put in the square root of 1 plus 16x squared. I want to close off my radical. The variable of integration is x from 0 to 2. So we get 8.4093. I'm also going to evaluate this integral. I'm going to put this in as 1/4. I'll just kind of put it in as I see it. Times the integral, the square root of 1 plus x squared. I'm going to close off my square root. X is the variable of integration from 0 to 8. Right, and notice we get the exact same value, 8.41. All right, so are there any questions about the first example? Okay, now one of the major parts for these problems are simply the ability to find the derivative for whatever function you're given, and then you must square it. Okay. All right, now we'll take a look at the arc length. Well, excuse me, that was arc length. Now we'll take a look at the surface area of revolution. All right, so if I go back to the lecture note page, and if we scroll down to the surface area of revolution, here is in essence what we're doing. We're taking that piece of arc length, blow this up a little. So notice here's the formula. And notice here's that piece of arc length, the square root of 1 plus the derivative squared. We're taking that arc length and we're rotating that arc length around an axis. So here's the surface area of revolution about the x-axis. Okay, so here again, you're taking that piece of arc length, you're revolving it around the x-axis. Here we're finding the surface area, not the volume, but the surface area, the area of surface. So that formula is given by the integral from a to b. for 2 pi times y. So notice there's two alternative formulas here. Y and f of x are one and the same. That is simply your function given. So it's 2 times pi times the function given times the square root of 1 plus the derivative squared dx. So now here's some stipulations. And the problems that we are dealing with, they're all revolved about the x-axis. Okay, but here are the conditions that are to be met in order to use the surface area formula. If you're revolving about the x-axis, your equation must be expressed in terms of x. The limits of integration are also on the x-axis. If you're revolving about the y-axis, the equation must be expressed in terms of y, and the limits of integration are also on y. All right, so let's take a look at an example. Okay, we'll take a look at number 7. So here we're asked to find the surface area of revolution. So notice this is not arc length, but it's surface area. I believe problems 6, 7, and 8 deal with surface area. The other problems deal with arc length. So here we're asked to find the surface area of revolution about the x-axis for the function y is equal to 3x plus 3 over the interval from 2 to 3. And we're asked to round the answer to 2 decimal places. All right, so in this example, we're going to find the surface area of revolution for y is equal to 3x plus 3 over the interval from 2 to 3. So we begin our surface area problems in the same manner in which we begin our arc length problems. The first thing we'll do is find dy dx. So we have y is equal to 3x plus 3. So if we take the derivative with respect to x for both sides, on the left-hand side we have dy dx. The derivative of 3x plus 3 with respect to x is 3. Next we'll find dy dx quantity squared. All right, so dy dx is 3. So dy dx squared is 9. All right, so the third thing we're going to do is substitute into the to the surface area of surface formula. Okay, so I'll kind of rewrite the formula here. So S is equal to the integral from A to B for 2 times pi times f of x times the square root of 1 plus the derivative squared dx. All right, so our integral from a to b, we're given this over the interval from 2 to 3. So the surface area is equal to the integral from 2 to 3 for 2 times pi times f of x. Now keep in mind that f of x is simply the function that we're given, 3x plus 3. So I'm going to put that in a set of parentheses times the square root of 1 plus the derivative squared, which is 9, dx. Okay. All right, so this is what we're actually going to put into the calculator. So I'll simplify this up just slightly. I'll just add the 1 and the 9. So we have s is equal to the integral from 2 to 3 for 2 times the square root of 10 times pi So notice I'm keeping that function in a set of parentheses times 3x plus 3 dx. Okay, so this is what we will put directly into our calculator. Right, so again, that's the integral from 2 to 3 for 2 times the square root of 10. I simply added 1 plus 9 times pi times 3x plus 3. Okay, so I'm going to just clear out my home screen. I'm going to bring up the function integration. So this is 2 times the square root of 10. So make sure you close off your square root times pi. I want to put a begin set of parentheses for my function. So that's 3x plus 3. You want to close off your function, comma, x is the variable of integration, and we're integrating this on the interval from 2 to 3. And we have our area of surface is 208.63. And just keep in mind that this is in square units since we're talking about surface area. Volume is measured in cubic units. Okay, even though the units aren't important, well, they are important, they're just not displaying the units. But just keep in mind that this surface area is a squared unit measure and volume is a cubic unit measure. All right, so any questions about those two examples for today? Okay, I'm going to go back to the, well, actually I'm going to start recording at this time.